Microcontrollers are everywhere in today's electronics community. By integrating many of the most commonly used ICs onto a single platform, the microcontroller is appropriate for almost any project. Although simple programs are fairly straightforward, some practice may be needed to really take advantage of all their capabilities. In the University of Utah's ECE6780 Embedded Systems course, we took a deep look at their capabilities, their architecture, and good design approaches when designing a new system with one. We looked specifically at STMicroelectronics' STM32F0 series, which features a 32-bit ARM core and a great set of peripherals and I/Os. After discussing and implementing topics like system modeling, bus interfacing, interrupts, timers, DACs, and ADCs, the class was assigned the task of incorporating a few of these capabilities into a creative and interesting project. We chose to develop a messaging application that relies on radio transmission to communicate. The objective is to send and receive text via radio frequencies on the 2-meter amateur band, and don't worry, we are licensed. The main idea is to have an intuitive user console which hands the controller our intended message. It then converts it into common low-level convention, more about this later, which a receiving radio can understand. The receiver reassembles the RF data back into the text for your buddy to read. To make it functional, we'll use a few peripherals, a UART interface, timers, and interrupts in particular. A good place to start is the user interface since it doesn't depend on a radio or delicate timing. To configure the Universal Synchronous Asynchronous Receiver Transmitter Bus, or UART, we modify the following. The board's pinout description shows that UART 3 on PC4 and PC5 won't conflict with any other pin requirements later. We need to enable the C bank of I/O pins in the UART clock. Pin PC4 is set to use the alternate function as UART 3 transmit, and PC5 as UART 3 receive. The baud divider register puts the bus symbol rate at 115/200. Lastly, we connect the bus to an interrupt routine to catch incoming characters. After a few test strings, we can use some creative character positioning to make an aesthetically pleasing menu. Further programming is needed to recognize ANSI escape sequences for arrow keys, highlighting current options, and configuring operation parameters. The finished menu shows an opening welcome screen, a setup page, and a messaging window, which highly resembles the reminiscent AOL Instant Messenger from yesteryear. The setup menu allows changes to our transmission speed on the fly, as well as character encodings. The character encodings can take many forms so long as the two controllers agree. A great example is Morse code, which transmits audible dots and dashes. Morse is based on 5 base signals to transmit all alphanumeric characters. A dot is a short burst of tone. A dash is a tone 3 times as long as a dot. A bit pause is an intra-character space, which is the same length as a dot with no tone, used to make dots and dashes distinct. A char pause is the inter-character space, which is as long as a dash with no tone, to signal that the preceding dots and dashes forms a character. And the word pause is the inter-word spacing, which is 7 times the length of a dot, to separate words as spaces do in writing. This convention can map any binary encoding where zeros become dots and ones become dashes. For example, the string hey, which in binary is 01001000 and so on, using the ASCII character table, this becomes dot dash dot dot dash dot 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 and so on. The sensitive variable in this semi-universal convention is the duration of signals, which can seem subjective if not confined to tight tolerances. Thus, a timer will count precise time intervals to drive the switching of zeros and ones. Before configuring the timer, some design specifications can help to specify its behavior. Morse time calculations are based on the Paris convention, which states that the word Paris contains exactly 50 of the base convention units. If sent 5 times a minute, 5 words per minute, that's 250 elements in a minute, or 240 milliseconds per element. An experienced operator can achieve about 20 words per minute. We'll calculate transmission speeds from 1 to 100 words per minute, with the shortest element being 12 milliseconds. Configuring the timer to count in increments of 0.1 milliseconds yields a 0.83% error due to the timer. Timer 2 of the STM-F0 is set up as follows. The default clock rate of 8 MHz is prescaled by 800, so instead of a period of 125 nanoseconds, we get 0.1 milliseconds. We enable the update interrupt in order to change GPIO as needed in the interrupt routine, and the timer interrupt priority exceeds the console interaction interrupt because of time sensitivity of the transmit and receive. The timer is disabled to start since we only want it when transmitting or receiving. At this point, it should be noted that encryption over amateur radio bands is illegal, and care should be taken to verify that your encoding is acceptable before transmitting. In this case, Morse is an acceptable method. To avoid introducing new variables during testing, we can wire two controllers directly to each other. This eliminates time delays between transmitter and receiver and avoids all the potential signal degradation and noise from the radio transmission. Once the sending side triggers the start of communication, the timer counts to the desired duration with the tone present or absent as needed. The receiving controller repurposes the same timer to count the duration of the tone signal. If we let B denote a pause between bits and a C is the pause between characters, the receiver might receive a series of signals like 0B1B, 0B0B, 1B, 0B, 0B, 0C for the H in our Hey message. The bits are transmitted most significant bit first to the receiver. Its job is to determine what the signal represents according to the timing and tone present/absent convention. Expecting the exact calculated durations is unrealistic in reality. Thus, we set up high and low thresholds for the signal's lengths. With a 25% tolerance, the signal can be 75% or 125% of the calculated speed and still be distinguishable. Once identified, a 0 or 1 is bit shifted into a tracking variable until the character is completed. After the whole string of characters is collected, it's printed to the messaging console and a notification appears on the integrated I2C LCD display. Using a direct link of controllers, we were able to reach speeds of up to 300 words per minute, although we were nearing tolerance limits. Now it's time for hardware and all the potential bugs that come with it. We'll be using a pair of Baofeng handheld radios which feature a common interface through its 2.5mm and 3.5mm jacks. We can open a carrier frequency, known as keying up the radio, by shorting the sleeves of both pins. The audible tone is fed into the ring of the 3.5mm pin with its reference connected to the sleeve of the same pin. We arbitrarily chose 1 kHz tone as the data signal just so that we could hear the tone for debugging. As a side note, it's feasible to generate the square wave using the controller's PWM timer modes, but this would have reinforced an already present ground loop problem which continuously tells the radio that you're wanting to transmit. That said, the connections to the radio were initially made with NPN BJTs to allow the controller's 3.3 volt outputs to drive a 5 volt signal into the radio. We later replaced the transistors with opto-isolators to help resolve the ground loop issue. It also helped prevent the transmission of noise from power supplies and wires being excited by radio waves. The receiving hardware centers around the LM567 tone detector IC, which provides a switch to ground when a tone is present within the specified passband. Simply put, a capacitor and resistor pair control a voltage-controlled oscillator, which sets the center frequency of the decoder. This VCO drives an I-phase and Q-phase detector pair whose outputs is either 0 or 1 by a comparator. A logical low is given when a signal is present within the bandwidth of the tone detector's passband and high otherwise. The bandwidth is set by external capacitors, and using the provided equations for center frequency in the datasheet, we connected a 0.1 microfarad capacitor as C1 to pin 6 and a fixed 11 kiloohm resistor with a fine trim potentiometer as R1 between pins 5 and 6. This yielded a center frequency of 977.77 Hz. Our initial impression led us to choose a narrow bandwidth, thinking this would filter out noise, but this apparently caused us poor response speeds. These slow speeds cause long fall times in the LM567, which results in missed signals from the transmission. After allowing a wider bandwidth, we selected C2 as 1 microfarad, which gave a bandwidth of about 8% on the center frequency, and mitigated the trade-off to get faster reaction speeds. With accurate and timely reactions to input tones, we can feed the radio's speaker output, which is the tip of the 2.5mm pin, to the LM567's input. The response time from triggering the transmitted tone to receiving the detected high or low signal was a whopping 40 milliseconds, which seems like a problem, but a delay from send to receive is actually acceptable. It just makes for a laggy conversation. Compression or stretching, on the other hand, would result in missed signals. In conclusion, this is definitely a feasible form of communication, and it might actually be useful if your smartphone falls in the toilet and you can't remember Morse code right away. Unfortunately, there is an upper limit to its speed, and although the controller could be prescaled to count at faster intervals, piping the transmission through a handheld radio is definitely the limiting factor. It may be slower than digital communication, but it does show potential in reliability.